Algebra 1 students, welcome to your 7.5 notes. Today we are going to be looking at rational exponents and radicals. I chose that song today because, A, I knew you'd hate it as much as I do, because we all know everything's not awesome. Okay, some things are, but that's what makes them awesome, is that not everything is. Okay, now, but in the same way, not everything is radical, but some things are, and we're going to be looking at some of those things today that are, in fact, radical, like this entire lesson. The big idea is first some terminology. The index, the radical symbol, and the radicand are things that you need to know what they mean. We're used to seeing square roots. What you may not be used to is seeing things like third, fourth, fifth, or 17th roots, or whatever they happen to be. The index is the number that we put right inside the little check mark portion of our radical symbol, and the index tells us what root we're discussing. The radicand is the number that we're working with, and you know what a radical symbol looks like. You may call them square root symbols. It's the same shape. The difference being, if it's not a second root, then it's not actually a square root. It could be a third or cube root or any other number. Now, really the big deal today that we need to make sure you understand is this relationship that you see here. It's a rational exponent. A to the m over n is the same as saying I'm going to take the nth root of a to the m power, or you could switch the order and say I'm going to take the nth root of a and then raise that whole thing to the m power. Now I know that's all in variable form. It's kind of weird seeing it that way, but we'll have a chance to take a look at this a little bit closer as we move forward. So let's do some examples just to understand what does it mean when our root is something other than 2. I mean, you guys know square root of 9 is 3, square root of 64 is 8. You've seen that kind of thing, but I don't know that you've seen some of these others. So here we go. The cube root of 27. The idea that we're looking at here is what number times itself 3 times x times x times x would equal the radicand, which in this case is 27. So what number times itself 3 times equals 27? In this case, we know it has to be an odd number. You could start trying different values. You'd realize pretty quickly, whoa, this has to be a small number. And in this case, the number is 3. So the cube root of 27 is 3. What that means is 3 times 3 times 3 equals 27. All right, number 2 is kind of a weird question in my opinion. What's the 17th root of 0? Well, what number times itself 17 times equals 0? There's only one possible answer there. That would be 0 times 0 times 0 dot 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 times 0. All right, number 3. This is an interesting one. The 5th root of 32. The fact that it's a 5th root tells me the number I'm looking for has to be pretty small. The fact that the number's 32 tells me it has to be an even number. You're not going to do a 1 to the 5th power, 3 to the 5th power to get there. It has to be even. And if you even tried something as small as like 4, you'd quickly realize, wow, 4 to the 2nd power is 16, 4 to the 3rd is already more than 32. The only option here is 2. So what that's saying is 2 times 2 times 2 times 2 times 2 equals 32. You could check that out yourself, count it on your fingers, try it on your calculator, whichever method you want to use, and you would find that the 2 times itself 5 times is exactly 32. All right, let's go to that big topic we were looking at now, where we look at the relationship between radicals and rationals. Okay, so rational exponents. I should be more specific. We're not talking politics here. We're talking exponents. We're talking math. We're talking, we're talking about x to the 1/2 right now. So x to the 1/2. The way we would write that in radical form is like this. It would be x to the numerator power, which is 1, and then the index is the denominator of that fraction, which is 2. Now, one thing to keep in mind, we know that when we see x to the first, we can just write x. And the other thing that we want to make sure you understand is that a square root is exactly the same as a second root. So you could write your answer like this and you'd be correct. This would also be correct, but it just has a lot less extra unnecessary stuff. All right, let's take a look at number 5. You'll note this time the exponent of 4/3 is applying to w, not 12. So my next step, I'm just going to rewrite the 12. I'm not doing anything with 12. Okay, so what I want to do then is put the radical symbol. W is inside, and the root or the index is 3. The power is 4. Now I'm going to show you 2 ways to write this. You could write it like that, or, and there's a little bit of a difference here, cube root of 3 and that whole thing raised to the 4th. Again, it doesn't matter if you do the root or the power first, you would get the same value. And why did I put a 3 there? Nobody knows that answer. How about a W? All right, sorry about that, folks. But the cube root of W raised to the 4th, or W to the 4th and take the cube root, you get the same exact value. All right, and we'll look when we get to numbers at which order we would want to do that in. And as a matter of fact, we'll run into that on this next question, number 6. Note this time that we have parentheses around 16z. That means this exponent of 5/4 applies to both terms. So I'm going to have 16z. The radical sign is around the entire, or over the entire thing. This time the root is 4 and the power is 5. And once again, you have the choice, do you put the 5 inside or outside? The answer is it doesn't really matter. But I'm choosing to put that 5 outside on purpose, and the reason is this. We're going to simplify 16 to the 5/4. Now what I know is this. I don't want to have to figure out 16 to the 5th power. I don't have that memorized, and I don't want to have to get out a calculator to get a number that big. So typically when we work with numbers, if you want to see if it'll work, we take the root, then the power. And I do know that the 4th root of 16 is 2. So really what I have here, I'm going to separate this. I'm going to have 2 to the 5th, and I'm going to have the 4th root of z to the 5th. And I can do one more step of simplification. 2 to the 5th is exactly 32. We just saw that on the last slide on one of the previous problems. And we can't do anything else with the z, so we would leave it like that, the 4th root of z to the 5th. And again, it doesn't matter if that exponent is inside or outside the radical, you would get the same result. All right, on problems 7 through 9, we have a similar but opposite process to what we did on 4 through 6. This time we're taking radicals and writing them in exponential form. So here we go. We have the 4th root of a to the 7th. I could rewrite that as a to the 7/4. And you know what we are right there? We are done with that problem. I like fast problems. I don't know about you. All right, let's take a look at the next one. 36 times x to the 6th, and we're taking a square root of the whole thing. So I'm gonna think of this as 2 separate problems. One of them is going to be the square root of 36, and the other one's going to be the square root of x to the 6th. Now remember, we said when you do a square root, there's a secret little 2 right there that you don't have to write, and yes, that's a 2. And we happen to know the square root of 36 is 6. And then what I can do is say, well, this is x to the power of 6, the root of 2, so that's 6/2, and we know 6 divided by 2 is 3. So that is 6x cubed. And you may think of different ways to simplify it other than what I just showed you. It's okay, but we should always end up with that answer if we're doing it right. All right, why don't you pause the video, do number 9 on your own. All right, welcome back. You can see my work on number 9. 16w to the 3/6 is where I started. I knew 3/6 was exactly the same as 1/2. And remember, a 1/2 power is a square root, so I knew that the square root of 16 was 4, and we're still multiplying by w to the 1/2. So right there is the simplified version in exponential form of number 9. All right, let's keep going here. We're going to apply some of the properties that we've previously learned of how you apply exponents, but now we're going to also change that result into a radical form. And I mean, it's obviously very radical to be this cool. So when we do x to the 2/3 times x to the 1/4, remember that's x to the 2/3 plus 1/4. We need a common denominator. Now you guys know how to do this because you've been adding fractions since about 4th or 5th grade, and so I'm not going to explain that process, but we need that common denominator, and in this case it's 12. We got 8/12 plus 3/12, and then finally we can add those together. We have x to the 11/12. That's great. That's where we would have stopped before, but this says to write in radical form. So we're going to go ahead and do that. I'm going to have a 12th root, that's lovely, of x to the 11th. There's my simplified version in radical form. All right, same idea, new numbers on number 11. So I'm going to have x to the 2/3. I'm going to apply this 1/3 before I go too far. 8 to the 1/3, that means cube root. And I know the cube root of 8, that's 2. And x to the 1/3, well, that's just simply x to the 1/3. Can't do anything else with that. And, well, what do you know? X to the 2/3 times x to the 1/3, that's x to the 1. So I have 2x. Now you'll notice the instructions here say to write in radical form. Folks, if there's not an exponent, you can't write it in radical form. There is no root. This is your number. It is simply 2x. All right, we have one page to look at some more simplification and changing forms. This time we're starting in radical and changing it to exponential. So on number 12, I want to actually simplify by changing these things into exponential form first. I think that's an easier way to do it. And I know this is a to the 7/5 power, which fortunately is exactly the same as the a to the 7/5 on the second term. The key to this problem is to notice that our variables are the same. It's a to the 7/5 for both. So if you have 4 of these and you subtract 6 of them, you'd be left with -2 a to the 7/5. And we are already in exponential form. We've made that adjustment, so we are finished with the problem. All right, we got just a couple more left. 13 is kind of a weird one. I'm going to go ahead and change this to exponential. B to the 1/3 minus b to the 4/3. You'll note that nowhere in today's notes or in previous notes have we talked about when you subtract powers from each other. There is no rule for this. What we have right there, folks, is a simplified exponential form subtraction problem. The variables are both b, but since the powers are different, it's just like if you have x squared plus x. You can't add those terms together. I just surprised some of you. I hope not. I hope you know that you can't add x squared and x. And in the same way, you can't subtract b to the 1/3 and b to the 4/3. That just simply will not work. All right, our last problem, number 14. I'm going to go ahead and change these again to rational exponents. So I'll have x to the 6/3 minus 3 times x. You got to be careful on the power here. Remember, there's like this little secret 2 right there. So this is to the 4/2. Now watch what happens here. 6/3 we know to be 2, and well, 4/2 is also 2, and what we have left then is -2x squared. Folks, I hope this lesson was not only radical but very awesome for you, and I hope you come to class ready to work hard and to get a good practice on these things. Have a great day.